Okay, in this problem, the goal here is to get some familiarity with how to use the equation for doing a stress transformation. So we'll see that it's actually pretty straightforward to use this equation. This example is a good illustration of how the equation is used and what each of the terms in the equation mean. So let's take a look at a composite material. So we're just looking at like a small cutout. This is a portion of a unidirectional composite structure subjected to some combined loading. That's what's sketched below here. So each of these fibers that you see, these are these lines that are running diagonally. I'll draw a few more in here. These are like the fibers in a composite material. So a composite material is an example of a material that would have strengths that vary based on the direction. So maybe a metal was what we would call isotropic. No matter which way it's strained, which direction it's strained in, a lot of metals will have the same strength no matter what. A composite though, however, it's going to have a strength that's probably measured in the fiber direction, so in this direction. It may also have a strength that's measured perpendicular to the fiber direction. That's typically how composite strengths are measured. And composites are outside of the scope of this course, but this is one example where it would be very much relevant, very much of interest to do a stress transformation. So using this example just to give you kind of a real life flavor. So let's say that we've cut out, that this is some portion of a composite structure that has been cut out, and say it's subject to some combined loading, and we're just zooming in at some piece of it. So just like we did in chapter 8, there's some combined loading. So if we have this stress element here, which I'll actually retrace it in red so it's easier to see, but let's say we have this stress element and we've done our combined loading, we figured out what the stresses are at this position in this stress element, and and over here we've summarized that. So we have a stress element over here in the right, okay? And our stress element, we found the stresses. It was convenient for us to find the stresses in the x and y coordinate system, okay? But what we really want to know is what are the stresses in the direction of those fibers, right? So in reality, those fibers are running at some angle. If we have our coordinate system for the we have our coordinate system for the structure, x and y. You can see that the fibers form an angle theta with respect to x. Okay, so what we really want to know is if this angle theta, this can form a new coordinate system, a rotated coordinate system, and we'll call that one x prime, y prime axes. So what we really want to get is stresses in the x prime direction, y prime direction. So for this problem, since we just want to know what are the stresses in the fiber direction, let's say we've calculated what the stresses are in the x direction because that was convenient. Now we need to rotate to get stresses in the x prime direction. Okay, so what we'll end up having is a stress element that's simply rotated, and we'll have some stress in the x prime direction. There will be a normal stress in the y prime direction, and there will be shear stresses that are also in this new coordinate system. Okay, so like I said, all of this is really just to set up the motivation for why we use the equation. Actually applying the equation, once you've derived your stress element over here, once you've derived the stresses on this stress element, it's really straightforward to use the stress equation now. Now you're virtually plugging it into the stress transformation equation. So once you've derived everything, you'll have that sigma x prime is equal to, and this is just the stress transformation equation in the lecture notes. Sigma x plus sigma y divided by 2 plus sigma x minus sigma y. Oops. Divided by 2 times cosine 2 theta. Forgive the penmanship here. Plus tau xy sine 2 theta. Alright. And we'll know what each of those variables are. Sigma x, sigma y, tau xy. You'll have calculated that for this stress element up here. And theta is the angle of rotation from the x-axis, going from x to x prime. That would give us sigma x prime. So in this case, that's what we're interested in, to get the stress in the fiber direction of this composite material.